Welcome viewers, in this video we will see the design of ripple or asynchronous counter design 4. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, design of ripple or asynchronous counter. We know that counter is a digital device is made up of flip-flop that will store the 1-bit data. We have two types, asynchronous and synchronous. Synchronous mean all the flip-flop receive the same clock pulse. Asynchronous mean first flip-flop receive the clock pulse. The output of first flip-flop is given as a clock pulse to the second flip-flop. So the second flip-flop operation based on the first flip-flop. So the operation is not synchronized. So that is called a asynchronous counter. It is also called as a ripple counter. Now we'll see the design. Design the ripple counter for the state diagram shown below. Based on the state diagram, we need to design the ripple counter. So it is from this is state different. There are 5 states available. 111 changed to 110. Then it goes to 101, 100, 011. Right? So the 3 digits available. So definitely there are 8 states will be there, but only 5 states are here we needed. Remaining 3 states is not needed. And also it is clear that it is a down counter. You start from 111 is keep on reducing 110, 101, 11, 100, 011. Right? So this is the 3-bit counter. 8 states are there, but in the state diagram only 5 states available. Remaining 3 states we need to disable, and also it is coming under the down counter. So based on that we can see the step 1, determine the number of flip-flops. So n equal to 8. We know that this 3 digits are there. So definitely n equal to 8. There are total 8 states will be there. So 2 to the power n greater than or equal to n. So that is the condition required. Based on the condition we need to identify the number of flip-flop. If n equal to 3, we will take n equal to 3. 2 to the power 3 greater than or equal to 8. So that is 8 greater than or equal to 8. So this condition is satisfied. So we need 3 flip-flops are needed. So totally 8 states will be there. But in that we are going to use only 5 states. Right. So here we can take n equal to 5 also. What we need is n equal to 5. So that 2 to the power 3 is, this will be 5. So for that case also this condition is satisfied. Right? Total 8 states, but in this state diagram only 5 states are there. So we will take capital N equal to 5. So based on this condition, 8 greater than or equal to 5. So this condition is satisfied. So we need 3 flip-flops are needed. The second one is we need to find the what type of flip-flop we are going to use. So here we will going to use the JK flip-flop. Any type of flip-flop can be used, but in this we are going to use the JK flip-flop. Now we will see the truth table. Based on the state diagram, we need to design the truth table. So this is the clock pulse available. C, B, A. C is the MSB, A is the LSB. Right? It's a down counter, so it is written in reverse order. N to 0. 111, 110 up to 000. So normally we will write from 0 to n, here n to 0. So in this the first 5 states are needed based on the state diagram. So the first 5 states are 1, 2, 3, 4, 5 are 1, remaining are 0. That is, this is the preset logic. We need to preset the flip-flop so that it will execute from 0 to 4. 5, 6, 7 minutes it will preset. Again it will start. If it is up counter, we will give the reset logic. 0 to 5, thereafter the flip-flop will be reset. But because of down counter, because of up counter, we are using the preset logic. Right? So up counter we are using reset logic. Down counter we need to use the preset logic. So that the preset, the flip-flop will be preset. Again it goes from the high level. So for the based on the state diagram, first 5 are high, remaining 3 are low. It is also, we can take it as mod 5 counter. Right? So it is clear that up counter we are using reset, down counter we are going to use the preset. Now we need to find the logical expression for this y so that we can give this preset. For that we are going to use the Karnaugh map. There are three variables. This is a three variable K map. C is represented in vertically, BA represented horizontally. C one variable, two possibilities, 0, 1, C bar C. BA two variables, four possibilities, 0, 0, 0, 1, 1, 1, 1, 0. B bar A bar, B bar A, BA, BA bar. Now we need to fill the columns. So it is from 0, 1, 2 is logical low. 3, 4, 5, 6, 7 logical high. So we know that these min terms are, if we represent min term, this is 0, 1, 2, 3, 4, 5, 6, 7. So 0, 1, 2 is logical low. 0, 1, 2. 3, 4, 5, 6, 7 is logical high. Right? So that totally 5 states will be there. So now we need to group this. So these four cells are grouped together. These two cells are grouped together. While grouping these four cells, we have to refer the corresponding second row. Second row is C. Similarly, corresponding columns. All four columns are covered. So B bar, A bar cancelled by BA. B bar A cancelled by BA bar. So all are cancelled. Only C is there. While grouping these two cells, we have to refer the corresponding first row as well as second row. First row, second row, C bar C is there, got cancelled. The corresponding column, third column, BA. So only BA. This row cancelled, only column is there, BA. So y equal to C plus BA. Since it is down counter, we need to derive the preset logic instead of reset logic. Right? Up counter means we are using reset logic. Down counter we are using preset logic. So that it will go from this 0, 1, 2 it will not execute. 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7 it will execute because of preset logic. Now we'll see the logic diagram. Based on the design, we'll go for the logic diagram. So we already discussed there are three flip-flops are needed. A, B, C. We are using JK flip-flop. The logic high is given to J input as well as K input. J also logical high, K also logical high. All three flip-flop receive the logic 1 as a input. Then what is the nature of JK flip-flop? If both the inputs are high, the output will toggle. The output, this present state and next state will toggle. Present state 0 means next state will be 1. Present state 1 means next state will 0. So this A will toggle. This is the output for every clock pulse because this is given as a inverter. So during every negative edge, this output will toggle. During positive edge, it will not toggle. What is positive edge and negative edge? So this is the clock pulse. This is positive edge, changing from 0 to 1. This is negative edge, 1 to 0. So during every negative edge of the clock pulse, this flip-flop will toggle because of both are high. What about the second flip-flop? The clock pulse to the second flip-flop is A bar is given as a clock pulse. If A is given as a clock pulse, there is a up counter, right? Because this is down counter, so that A bar is given, right? A given means up counter, A bar given means down counter. So during this the negative edge of this A bar, this B will changes. B will toggle for every negative edge of A bar. Similarly, this third clock pulse third flip-flop will receive the clock pulse from B bar, right? So every negative edge of B bar, C will toggle. So that this first flip-flop depends upon clock pulse, second flip-flop output depends upon A bar, third flip-flop output C depends upon B bar. So the operation is not synchronized, so that it is called a asynchronous counter. So every negative edge of this clock pulse, the output of the first flip-flop A will toggle. Every negative edge of the A bar, first flip-flop output A bar, the second flip-flop output B will toggle. Similarly, every negative edge of B bar, C will toggle. Now because of down counter, we are using the preset. Preset also logical low. We need to give the preset logic based on the expression what we discussed. C plus AB. That is the preset logic we obtain from the K-map. So C plus AB we need one OR gate. C is connected. A into B we need one more AND gate. So A and B is connected. So here AB will come. So AB plus C done by OR gate, that is given as a preset logic. So for from the 7 to 4 it will execute. 5, 6, 7, that is the flag pulse, that is 0, 1, 2. These three will be preset. So it will go for the down counter, start from the 7, 6, 5, 4, 3. Thereafter it will reset. Right? First 5 states will be executed, remaining 3 states will be preset. So in this video we discuss the design of ripple counter using the state diagram. In the state diagram 5 states are there, and also we can 3 digits, and it's coming under down counter. So we discussed based on the condition, we decided 3 flip-flops are needed. Then we discussed the truth table. What the given 5 states are 1, remaining states are 0. Based on that we obtain the logical expression for preset because of down counter. That preset is implemented in the logic gate. We are using JK flip-flop. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.